Hello, in order to do your homework this evening, you need to know a little bit about what is called Leibniz notation. So Leibniz notation is a little weird, but let's walk through it and it should be no problem. So we've been working with the tangent line approximation, which we wrote as f of x is approximately f of a plus f prime of a, which is the derivative, times the difference between x and a. So we could rearrange this and say that, well, f of x minus f of a is approximately equal to the derivative f prime of a times times the difference of x and a. Now, f of x minus f of a is the difference between two different outputs, right? So I plug in x, I get something, I plug in a, I get something else, and then this is the difference between those two. So I could write that as delta f. So you've probably seen deltas a lot when you were doing science. You see it a lot in physics, you see it a lot in chemistry. In math, we use delta the same way. Delta just means some value minus another value. So that is an increment. Now, in this case, we can say it's delta f, or we could say it's delta y, right? Typically, we write things as y equals mx plus b. And y is the function. So delta y is just the two different y values from plugging in different x values, which means that x and a are two different x values. That's why we end up with this delta x if we're talking about x minus a. So if we keep rearranging this, we actually will see that f prime of a could be written as delta f over delta x, or just delta y over delta x, which we've seen before. This makes perfect sense, right? We have said that a derivative is essentially the same as the slope of a function at a particular point, right? So delta y over delta x, change in y over change in x, is what we have seen in the past for slope. So this makes perfect sense. You could even expand this and see that f of x minus f of a over x minus a looks a lot like calculating a slope. So we have a couple other words to add to this, however. If we have x greater than a, we would call that a forward difference. And if x is less than a, we would call that a backward difference. Just in case these terms show up again. So anytime you see this delta f over delta x, that is like calculating a slope between 2 points. However, a derivative does not necessarily have to exist between 2 points. It can exist at a single point. And so for that, we kind of want to introduce this new notation that is due to a fellow named Leibniz, a very famous mathematician. He helped invent calculus, essentially. And we would rewrite this derivative, f prime, as df dx. So you read that as df dx. There's no need to say divided by or over anything. You would just simply read it as df dx. So df dx is simply another way to write the derivative of f. Now this is specifically the derivative of f with respect to x. That's why there's that x at the bottom. So if we write df dx, we are writing the derivative of f with respect to x, which is fine because we're typically always with respect to x, at least for right now. Now, a new piece of this notation is that you've lost the parentheses. You don't necessarily know if it's f prime of x or a or 9, so you have to introduce a slightly different notation to say where you are evaluating or computing the derivative. So we do that with a vertical line on the right-hand side of our df dx, and we write where we are computing or evaluating it at the bottom of that line. So I could write df dx at the x value equal to a, just like this right here. You could also write df of a, and you would still simply understand that to be the derivative, df dx, at some value a. So both of these are acceptable ways to write that. So This may seem like a little bit too much initially, but once you have multiple variables going on, this is the best way to write it. So hopefully it makes a little sense. All we're doing now is we're having a different notation called Leibniz notation for a derivative. Now, one other thing that's important is don't necessarily think df dx as a ratio, but think it as an operator. So you see right here, I'm going to highlight this in red again, that you have d dx. So d dx means to take the derivative of something with respect to x. So if I write d dx of f, that is the same thing as taking the derivative of f with respect to x. So right now, just think of d dx as a new operation, like multiplying or dividing. And that operation is the derivative of something. So the first part of our homework is from the textbook, numbers 1 through 4, and this is simply to write several things in Leibniz notation. So write in Leibniz notation. So, first one, number 1, I'm going to write the cost of a steak, C, and that's in dollars, is a function of the weight, W, of the steak in pounds. So, I have I have C as a function of W. So, what I'm doing here is I'm just going to write the derivative of this in Leibniz notation. So, W is the dependent variable. It's like x for us. So, this is like x. And then the C for us is like our y, or our f. So, in order to write this write the derivative of this as Leibniz notation, we would simply write dc dw. Now make sure you use the exact same variables, in this case uppercase letters, for your answer. Number 2. The distance to the ground in feet of a skydiver is a function of time in minutes. So I have d as a function of t. So my derivative in Leibniz notation would be d dt. Now, number 3, an employee's pay is a function of the number of hours worked. So this is p as a function of h. So my Leibniz notation for the derivative would be dp dh. And finally, number 4, the number of gallons of gas left in a tank is a function of the distance in miles the car has been driven. So this is n as a function of d. So my Leibniz notation for the derivative of this function would be dn dd. So this is quite simple, honestly, if you look at it. You just need to know what is the variable for the function, so your y or your f, and what is the variable for your x. So this is our dependent, this is our independent. For the questions from the handout, we'll be doing tangent line approximations again. However, this time our function and the function for the derivative have changed. So instead of a square root, we now have a cube root. So we are going to be estimating the cube root of 24 based off of the tangent line approximation at x equals 27. So based off of the cube root of 27. So first things first, I'm going to quickly remind you that the tangent line approximation comes from f of x is approximately equal to f of a plus f prime of a, the derivative at a, times x minus a. So first thing I'm going to do is compute the value for my derivative, f prime of a. So f prime of a is equal to, now this is given up above, 1 over 3 times the cube root of x squared. Or sorry, a squared. So you should not use a calculator for this. So if you need to do some napkin math, I'm going to do some napkin math so we can do it together. So this is a little tough to do, but we'll go ahead and do it. So we have, if we want to do f prime of 27, then we're going to have 1 over 3 times the cube root of 27 squared. So when we do this, we can do this actually in any order. So we can do the 27 cubed and then squared. So what does that mean for us? Or cube rooted then squared. So that means we can do 1 over 3 times, well, the cube root of 27 is 3. So that'll be 3, then still squared. So 3 squared is 9. So this actually ends up being 1 over, our derivative value will be f prime of 27 will be 1 over, so this is 9 times 3, which is 27. So my tangent line approximation, so f of x is going to be 24. So we're approximating the cube root of 24. Is going to be approximately f of a. Well, f of a is going to be the cube root of 27. So in case you've forgotten, f of x, or our function, is cube root of x. So it's cube root of 27 plus f prime of a. So we just found that to be 1/27 times the difference between x and a. So x is actually going to be 24 and a is 27. So the approximate value for our cube root of 24 is going to be the cube root of 27, which is 3, plus 1/27 times -3. So that's going to be -3 over 27, which I can simplify. So that is 3 plus, or I guess I should say 3 minus at this point. So simplifying this, both of these divisible by 3, that would be -1/9. So my function's approximately, so my cube root of 24 is approximately 3 minus 1/9, or 2 8/9. For the next question, we're going to be using the tangent line approximation again, but this time we're going to be approximating the cube root of 72 based off of the cube root of 64. So again, we're starting with f of x is approximately f of a plus f prime of a times x minus a. So I'm going to start with finding out the value for f prime of a. So f prime of a, again, is 1 over 3 times the cube root of a, did the same thing, a squared. So f prime of 64 is going to be 1 over 3 times the cube root of 64 squared. So again, you can do this in either order. You can cube root first and then square. So I'm going to do 1 over 3 times, well, the cube root of 64. Let's see, square root is 8. So let's see, cube root of 64 is going to be, but that doesn't help us. So let's see, cube root of 64, that is 4. So right, 4 times 4 is 16, and 16 times 4 is 64. So the cube root of 64 is 4. So I have 3 times 4 squared. And so f prime of 64 is actually 1 over 3 times 16, which is 48. So for my approximation, f of 72 is going to be approximately equal to f of a, which is going to be the cube root of 64, plus f prime of a, which we just found to be 1/48, times the difference between x and a. So that's going to be 72 minus 64. So f of 72, so the cube root of 72, is approximately equal to 4 plus So 72 minus 64 is 8, so that's 8 over 48, which we can simplify quite a bit here. So we can divide both by 2, that would be 4 and 24. We can divide that by 2, that'll be 2 and 12, so 1/6. So my actual estimation will be for the cube root of 72, 4 and 1/6. For question number 3, we're going to again begin with the exact same statement of our tangent line approximation, which is going to be f of a plus f prime of a times x minus a. So first we're going to start by finding our derivative value. So f prime of a, again, for a cube root is 1 over 3 times the cube root of a squared. So f prime of, so a in this case is going to be of our own choosing. So we're not given a value for a. So we have to figure out what a is. So what is the closest perfect cube to 100? So let's go through our list of perfect cubes, if anyone knows any. So we just did 64, right? So 4 cubed is equal to 64. So what's 5 cubed? Well, 5 cubed, so 5 times 5 is 25, and 25 times 5 is 125. So which of these two is closer to 100? Well, 64 is 36 away, and 125 is 25 away. So we're going to use a value of 5 for our a. So we want to find f prime of, sorry, not 5 for a. It should be 125, because a needs to be the actual cube. So that will be a is equal to 125. So f prime of 125 will be equal to 1 over 3 times the cube root of 125 squared. So again, any order. So I can say this is 1 over 3 times, well, the cube root of 25 is 5, so this is 3 times 5 squared. So our f prime of 125 is going to be equal to 1 over 3 times 5 squared, which is 25, so that's 3 times 25, which is 75. So 1 over 75. So going to our approximation. So f of 100, so this is approximating the cube root of 100, is going to be the cube root of our a, so that's the cube root of 125, plus our derivative of 125, sorry, at 125, which is going to be 1/75, times the difference between x and a. So x, in this case, is 100, minus our a, which is 125. So f of 100 is going to be approximately equal to, well, cube root of 125 is 5, plus, so this is negative 25 over 75. So my actual estimation will be 5 minus 1/3, or about 4 2/3. For our final one, we're going to be estimating the value for the cube root of 150. So f of x, we're starting with the same part, is approximately equal to f of a plus f prime of a times x minus a. So again, we are not given an a value. We have to figure that out. So from our problem we just did, we said 5 cubed was 125. So that's pretty close. Let's go ahead and check 6 cubed. So 6 cubed, so 6 times 6 is 36. And 36 times 6 is 180 plus, so that's 216. So it appears that we're going to be using the 5 cube again. So our a will be equal to 125. So thankfully we just did a lot of work involving this, but we'll go ahead and do it again just for practice purposes. So f prime of a is again 1 over 3 times the cube root of a squared. So f prime of 125 will be equal to 1 over 3 times the cube root of 125 squared. So again, you can do this in any order, and I could write that as, so 1 over cube root of 125 is 5, and then 5 squared, so this is 1 over 3 times 5 squared. So my derivative at an a of 125 is 1 over 75. So now we go back to our approximation. So we have f of 150, which is what cube root we're approximating, is approximately the cube root of, so our a value we chose was 125, because it's the closest perfect cube, plus our derivative at a, so that's 1/75, times the difference between our x and our a. Anyway, so that'll be x minus a, so that will be 150 minus 125, so that'll be 25 in the end. So our function will be approximately 5 plus, in this case, positive 25 over 75, which hopefully you recognize as a third. This actually bothers me. Keep it the same lines. So our actual approximation will be about 5 1/3, or 5.333333.